In this lecture, we find the solution of first and second order homogeneous differential equations. To find solution of first order homogeneous differential equation, we write firstly, the first order homogeneous differential equation is dy by dx plus p of xy equal to 0. To find the solution of this equation, firstly we separate the variables x variable and y variable separately, and then find what is the next term you get. After separating the variables, the equation is g of y dy equal to f of x dx. Now what is dy by y? Here if we write the equation dy by dx equal to minus p of x y, then y term we take on one side, dy by y equal to minus p of x dx. This dy into 1 upon y, that we write g of y dy. Since 1 upon y we replace by one function g of y dy equal to minus p of x dx. Minus p of x, we represent a function f of x dx. Now this is the equation we write in terms of the separate variable, y variable and x variable. If we integrate this equation, we get the solution. After integrating, integration g of y dy equal to f of x integration f of x dx plus c, where c is the constant of integration and it is the arbitrary constant. Then the general solution is the first order homogeneous differential equation. There is only one arbitrary constant c. Since this is a first order, once we get the in terms of the arbitrary constant, the general solution of the equation is y is equal to c e raised to alpha x. Now we see one example how we find the solution of such a first order homogeneous differential equation. In that example, we write the equation dy by dx plus x square y equal to 0. It is in that same form of that equation. That equation is first order homogeneous differential equation since other side equal to 0. As per earlier discussion, firstly separate the differential equation into two separate variables x and y. The equation is dy by y equal to minus x square dx. The next step is integrate on both sides. Integration is dy by y equal to minus integration x square dx plus constant of the integration or the arbitrary constant c. Then what is the integration? 1 upon y dy. This is the log y equal to integration dx x. Hence we write the next equation is log y equal to integration of x square dx is x cube by 3 plus constant of the integration log c. This log c take on the other side. Therefore we get the log y by log c. That term we write, if we cancel the log on both sides, y by c is equal to exponential minus x cube by 3, or c take on that one side. The equation is y is equal to c into exponential minus x cube by 3, and this is the general solution of the first order homogeneous differential equation in a given example. Means the general solution has only one arbitrary constant for first order equation, and the solution must be in the form y equal to c e raised to alpha x. Such a differential equation is also solution in the form y is equal to c exponential minus x cube by 3. Now we see the second order homogeneous differential equation and its solution. Find solution of second order homogeneous differential equation with constant coefficient. The general form of the homogeneous differential equation is d square y by dx square plus q of x dy by dx plus q of x y equal to 0. We write this equation in the form of the constant terms. That constant we choose, p of x is constant a and q of x replaced by constant b. The equation is d square y by dx square plus a dy by dx plus by equal to 0. Say this is the equation number 1, and in the form of linear operator, that linear operator we write d by dx is capital D, therefore d square by dx square becomes equal to d square. Therefore equation 1 in terms of the linear operator is d square plus ad plus b, outside y we take common and we write outside, equal to 0. Equation 2 is also the same form of the second order homogeneous differential equation. It is in terms of the linear operator. Now we write the quadratic equation or the characteristic equation. That equation is d square plus ad plus b equal to 0. Right? This is the next equation number 3. This equation is also known as, it is an algebraic equation. The equation 3, we find the roots of the equation. The roots of the quadratic equation is, we find, since this is the quadratic equation, d square plus ad plus b equal to 0. So the coefficient of d is 1, coefficient of d is capital A, and coefficient of here this next last term is b. Therefore the roots, two roots we find, these are small a equal to minus b, that value according to that equation we write minus a plus minus, plus term we write here for a and minus term for b, plus under root a square minus 4b divided by 2. These are the roots of equation 3, and b is minus a minus under root a square minus 4b divided by 2. As we know the root of the equation 3, then we find the solution of the equation 2 or equation 1. That solution we find for different cases. In the case first, if this a and b are real and unequal, then what is the solution of the equation 2 or equation 1? We find separately. In second case, if a and b are equal, then what is the solution? That also we find here. And in the third case, if a and b are in the form of complex number, then the solution of the equation 2 or equation 1 we also find here. In case 1, if the roots are real and unequal, that is a is not equal to b, then equation 2 becomes, equation 2 is d square plus ad plus b bracket outside y equal to 0. That equation written as d minus a d minus b y equal to 0. Here we write the two equations like d minus a y1 equal to 0 and d minus b y2 equal to 0. Both equations, both terms are in the form of first order homogeneous differential equation and their solution which contain one arbitrary constant. Therefore, the solution of d minus a y1 equal to 0 is y1 equal to c1 exponential ax, and d minus b y2 equal to 0 has solution y2 equal to c2 e raised to bx. Therefore, the general solution of the equation 1, we write y equal to y1 plus y2. Where y1 is known, y2 is known, substitute here and we get y equal to c1 exponential ax plus c2 exponential bx. This is the general solution of the equation 1, write as equation small a. Then also we find if the roots are real and equal, then what is the solution of the equation 1? Similarly, we also find if the roots are in the form of the complex number, complex term, then what is the solution of the equation 1? That we discuss here. In case second, if the roots are real and equal, that is a equal to b, then equation 2 written as d minus a into d minus ay equal to 0, since both a and b are same. Hence we write d minus ay equal to 0. Here we write one of the term d minus ay equal to 0. Then what about the second solution? That also we find here. D minus ay equal to 0. Its solution is y1 equal to c3 exponential ax. Then what about the second independent solution of this equation 2? For that, d minus ay we substitute for x, and the equation 4 we write in terms of, if we d minus ay is x, then we get this is one of the term, and the equation 4 becomes d minus ax equal to 0, and we say the next equation 6 here. D minus ax is again in the same form, therefore solution is x equal to exponential c4 into exponential ax. X we substitute here in the equation 5 and we again simplify. X equal to d minus a y equal to c4 exponential ax. Means d minus a y equal to c4 exponential ax. What is d? D is the linear operator, that is d by dx of y, means dy by dx minus ay equal to c4 exponential ax. Equation 7 is first order linear differential equation, since other side is non-zero term. If it is 0, then it is homogeneous, but here equation 7 is linear differential equation, other side is c4 exponential ax. Hence, firstly we solve the solution of the first order linear differential equation. Why we solve this equation? Since we firstly find what is the integrating factor, and using that integrating factor we find the solution of the second order differential equation. First order linear differential equation, its solution is obtained as, firstly we write the equation 7 in homogeneous form. and find the integrating factor. Equation is dy by dx minus ay equal to 0. First order homogeneous differential equation. Using that equation, we firstly find integrating factor. How we find? Separate the variable terms. Dy by y equal to a dx, and then integrate. Integration dy by y equal to integration a dx. Integration d1 by y dy is log y equal to ax plus constant of the integration c, log c. Log c we take on the other side. Therefore, we get the y by c, log y by c equal to ax. Cancel the log. Therefore, y by c equal to exponential ax. Therefore, y is equal to c into exponential ax. Here, in that equation, for first order homogeneous differential equation, y is equal to c e raised to ax. That term integrating factor is exponential minus ax. In the integrating factor for that equation is exponential minus ax. That integrating factor we multiply to the equation 7. Equation 7 you know. Here we multiply integrating factor to the equation 7. Equation 7 is dy by dx minus ay equal to c4 exponential ax. Now multiply integrating factor. Integrating factor is exponential minus ax on both sides of the equation. The equation is exponential minus ax bracketed term dy by dx minus ay equal to c4 into exponential ax into exponential minus ax. On the one side of the equation, this is an expansion of d by dx into bracket y into exponential minus ax. If we simplify that term, we get the original term. Other side is as it is, c4 exponential ax into exponential minus ax. Now integrate on both sides. We get integration is d by dx of y exponential minus ax equal to integration c4 exponential ax into exponential minus ax dx. Here is plus exponential minus exponential. It get cancelled and integration with respect to c4 dx plus constant of the integration. Next constant integration we write c5 and simplified term we get y exponential minus ax, since derivative integration of the derivative term is y into exponential minus ax equal to c4 integration c4 dx is c4x plus constant of the integration c5. This exponential term we take on the other side, therefore it gets denominator. Denominator term is exponential minus ax. If we take the numerator, equation is y is equal to c4x plus c5 exponential ax. This is the solution of the second order homogeneous differential equation in terms of the arbitrary constant c4 and c5. In terms of equation A is in terms of the constant a and b. Case third, we see if the roots are in terms of the complex number, then what is the solution of the equation 1? Now we see case 3. If the roots are in terms of the complex numbers. Complex term is alpha plus I beta and its complex conjugate is alpha minus I beta. That is, A is equal to alpha plus I beta. This is the root of the second order differential equation. If that equation is in the form of the auxiliary equation, or we say the roots of the quadratic equation, A and B both are in the form of complex term, and the complex conjugate is alpha minus I beta. Put these two roots and find what is the solution of second order differential equation. The solution is y equal to c6 exponential alpha plus I beta x plus c7 exponential alpha minus I beta x. C6, C7, these are the next arbitrary constant for the case 3. Here exponential alpha x for both the terms we take outside and we write the equation y is equal to exponential alpha x into bracket c6 exponential I beta x plus c7 exponential minus I beta x, where exponential I beta x we write in terms of cos and sine. Exponential I beta x cos beta x plus I sin beta x, and exponential minus I beta x equal to cos beta x minus I sin beta x. Put these two terms in the bracket and simplify. We combine cos term and sine term. We rewrite y is equal to exponential alpha x into bracket c6 plus c7, outside we write cos beta x plus I c6 minus c7 sin beta x. Here c6 plus c7 is one of the constant. That constant we write capital A1, and I c6 minus c7 another constant b, that we write b1 sin beta x. Therefore, y equal to exponential alpha x into bracket a1 cos beta x plus b1 sin beta x is the required solution of the second order homogeneous differential equation if the roots are in the form of complex term. Earlier we find if the roots are equal and real, then solution is different. Similarly, if the roots are real and unequal, then that solution is also different. Hence, these three terms we use how to solve the differential equation, it depending upon if the roots are equal or unequal or in the form of complex terms. Now that term equation is useful to solve any kind of the differential equation, whether it is in the first order equation or second order homogeneous differential equation. Thank you.